assigned somebody ID to, right? Or it detected a second human shape. It doesn't have to be concurrently two humans. It's just detected somebody in as player number 2 is what it is. So let's just see how it is. Now, if a person is a human, let's color them differently. Let's color them. Right now we are using black, blue, green, and red. Let's use white maybe. Where for white I need to take the red. I have to basically make everything 255. So green and right, okay. So the first player it detects is going to be all shown up in white. And how about the next player it detects can be all shown as, what is red and green, or green and blue? I don't know. How about maybe, let's just do 128 to everything, so there'll just be a shade of gray or something, right? Okay, so now here's what I expect. When I run the app, it's gonna run just fine. When I walk in front of it, it's gonna work just as before. Right now I'm blue. But if I move a little bit back, as soon as it can see my knees, it'll detect me as human, and instead of me becoming green as before, I should turn white, right? If the detection thing works. So let's see. I walk a little bit, I become green, and I became red, which is weird because that means the detection didn't work. Let's see why.
Color index.
Color index. Thank you so much. You guys are helping me a lot, seriously. Okay. And let's do this. This would have been pretty cool. The top left pixel alone might have been white and everything else would be the same color. Okay, let's try this again and hope that it works. I should be blue. If I step back a little, I should turn green, and now I think I should turn. I should have turned white at this point. Come on. Okay, help me figure out what went wrong. Let's see. Okay. Is it? The flags right here? Oh, you think it's initialization flags? Actually, if that had been a problem, it wouldn't have run even, right? Let's see though. Okay, so the initialization, it's depth and player index, then when it's open, I'm just gonna do, yeah, I want depth, I've got depth and player index, depth frame ready, that's fine. And depth frame ready, I come in and check for the P image, all this is fine, this is fine. You know what, let's do this. Let's set a breakpoint. Let's set a breakpoint. I wanna see what happens here. I wanna see the result of this. So I'm going to set a breakpoint here to see if the code ever falls. Well, it's always going to fall in 0. Well, yeah. I don't think the code ever gets in here at all. So let's F9 it. Let's see if the code gets in there. I don't think it does, but... Oh, wait, something happened. I became gray. How is that? And see, now I can go up or down or whatever. And it lost the player, and now it came and fell in here, which is really, really weird. Because now it's working. Hello? Okay, let me remove the breakpoint. And maybe I think I should face the Kinect and walk. So you guys can tell me if I become white, because I think my face is turned away. Okay, I'm going to face. This is the buggiest piece of code ever. Okay. All right. We're going to do one last code review and see what the problem is. Because last time it fell through. Okay, so what are we doing? Yes?
The index is not sometimes you jump into index 5. So,
Yes, 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 yes. I can't believe I didn't think of it. Thank you so much for that. So basically what's happening is because I used a switch, I'm only checking for 0, 1, and 2. Let me do this. I'm going to default it because the value, like we said, is going to be between 0 and 6 for 10 minutes. Okay, the value is going to be between 0 and 6. We're only looking for 0, 1, 2. In all the other cases where it's, where the value becomes 3 or 4 or 5, we're just basically not doing anything, which is what, thank you so much for that catch. Now if I default it, worst case scenario, if I'm not even detected as number 1, I'll still end up becoming gray as soon as it detects a human character, right? So, let's try it again one last time. There it is, I became gray, which is fantastic. Now I can walk wherever, and now I'm player 1 again. Haha. When you go out of the frame and when you come back in, it'll detect you as, see, now I'm gray again. So this is a way for it to keep, what's happening is it'll keep assigning the next player number. Now it should become gray. Okay, 1 out. I think I have to do a lot of grays now because, for 4, 5, 6. And now if I keep doing this, ultimately I'll become white. It's a good workout. There it is. So that's your human detection. But here is the really cool part. Shall I show you the really cool part? Here's the world's cheapest green screen technology if you want. If I comment out all of this, oops, what did I just do? Okay, the world's cheapest green screen is as below. Okay, if I just Control X it. You see, it completely segments the background out, and it only presents the human. So what you can do at this point is you can render whatever background you. Does that make sense, what I just did? So this basically is the simplest way to achieve green screen functionality using Kinect. So since the background is completely black, and since you are generating it, you can throw in whatever image you want. And one of the best ways to do it is if you take if you have an existing image that you want to overlay as the background, you can actually use a class similar to bitmap source and actually break it down pixel by pixel and read the color image pixel by pixel. And in this code, where we are generating random colors, you can actually substitute those colors, right? So it's a really, and it works beautifully actually. It's a really effective way to do green screen technology. And now somebody showed me I had 10 minutes left. So what I'm going to do is I'm going to basically show you 5 minutes left. Okay, I'm going to show you one last demo with skeletal tracking. And if I show you that, I've pretty much shown you everything there is in the camera aspect of things. To turn on skeletal tracking, it's very simple, right? Just like how we turned on color and depth in player index, I can just say or and do runtime options dot use skeletal tracking, right? And what this is going to activate is the whole skeletal tracking pipeline inside Kinect. And since skeletal tracking is not a raw stream, I don't have to open anything, right? This just activates it. I don't have to open it. So what I can do now is I can come in and directly handle the event for skeleton frame ready, right? Just like for video and depth frame ready. And I'm just going to say plus equals tab will generate the new event handler for me. And let's come in here. And let's look to see how similar the code is. In the past, we would get from E, we would get image frame. Now if I do E dot, you see I get skeleton frame, right? So I can do things like skeleton, and skeleton frame is of type skeleton frame. So I can do things like skeleton frame, S frame equals E dot skeleton frame. And if I see what I get from S frame, you see I get this collection right here called skeletons, right? I also get a bunch of other things. I also get things like, the frame number and timestamp as before. If I want to synchronize skeletons with the other subsystems, depth and video, I can do that. I also get something called the floor clip plane, which basically, so when Kinect looks at skeleton tracking, it tells you, it has to identify where the floor is, and the skeleton is sort of the normal from the floor. So in sort of an angled situation, Kinect will tell you which is the floor clip plane. So is it like a horizontal plane, is it a vertical? It's like an angled plane and stuff like that. So if you're seeing errors in skeletal generation, and that is because of a situation like this where it's a non-flat surface, then check out floor clip plane. But for the most part, you don't have to worry about this. And finally, you get something called quality, which basically tells you the quality of skeletons generated, which we'll look at in a second actually. But the most important attribute here is the skeletons collection. So what I'm going to say is, let's collect that in the skeleton data collection. I'm going to call it all skeletons equals sframe.skeletons. Now, when I have a collection, I can always run through it. Now, by default, the Kinect, just like the depth frame, can identify up to 6, humanoid characters on the scene, and it can make 6 skeletons out of the 6 humanoid characters. So I'm going to run a for each loop for actually let's just do a for each skeleton data skeleton and all skeletons. So at this point, it's going to look for each skeleton. Now, here's the interesting part. Whether or not it sees skeleton data in the front of the sensor, it'll return 6 skeletons, right? The way you determine if it actually is seeing a skeleton or not is by checking for skeleton.tracking state. Because the tracking state is going to be one of these options. Not tracked, position only, or tracked, right? If it doesn't see any skeletons, for all 6 skeletons that it returns, it's going to say not tracked. If it sees skeletons in front, if it sees a human character that it can skeletonize, it will basically set the tracking state as tracked. But if it sees more than 2 people at the same time, then it cannot do skeletal tracking on more than 2 people. So if it sees, 4 people in the scene in front of it, for 2 people, it will return a state of tracked, and for 2 more people, it will return a state of position only. Does that make sense? It will track the positions of up to 6 people, right? Where you are in terms of X, Y, Z. It'll track one position of the center of gravity of your spine for 6 people, but for 2 people, it'll give you 20 joints across your body, right? But since I'm only interested in tracking one person, I'm just going to look for a position of track. So I'm going to say if skeleton.tracking state equals skeleton tracking state.track. So at this point, I can grab from the skeleton collection a bunch of things. I can grab the overall skeleton's position, right? Whether or not they're tracked or just position. But if they're tracked, I can get their entire joints collection. So if you look at joints collection, you see all these 20 joints, ankle left, right, elbow left, right, foot left, right. I can get this whole collection. So I can do something like, I can get the head joint, and from there I can grab the position of the head. And it's going to return the position to be in X, Y, and Z. The interesting thing to note is while the depth camera returns position in meters, the skeletal tracking returns the depth camera returns the position in millimeters. The skeletal tracking returns the position in meters, right? So you will get the value between +1 and -1 for X and Y, like between +1 meter and -1 meter for X and Y, and Z will be all positive because you're in front of the Kinect the whole time. So I'll show you a quick example of what I'm talking about in the next 2 minutes. So instead of all of this here, I'm going to go to my toolbox, drag a canvas. I'll show you why I'm using a canvas, because a canvas is easy to create positions with. Okay, now let's go into properties of the canvas, set the background to a solid color. I'm going to do is I'm going to have Kinect, not just, we saw how it could track all of me and bring the things up. I'm going to take 3 more minutes of your time, even though we're officially out of time. We saw how the Kinect can track all of me, but it couldn't make out where my head is, where my shoulder is. Now we're going to do that. Now we're going to basically have Kinect see me, but then break me down into my head and my hands. So my goal is going to have this ellipse follow my head, and these 2 smaller ellipses follow my hands. That's the goal, okay? So let's go into the code. Before we go into the code, let's call these different ellipses head. This ellipse is going to be left hand maybe, and this should be the right hand. Okay, sweet. Actually, it should be the reverse, I think. It doesn't matter. I mean, the ellipses can travel. Okay. So head left and right. Okay. So what I'm going to do is take the position of my head, and if you look at what position sends out, it sends out a bunch of things, but most importantly, it's X, Y, and Z. You might be wondering what W is. W is a probability measure of between 0 and 1. The value of W can be between 0 and 1, and it's the probability estimate that Kinect is sending you of the position of that joint being at location X, Y, and Z. So if it can see that particular joint, if it can see the head in this case, it'll assign a W of 1, right? But if it cannot see my head, it can only see neck down, it'll still return an inferred XYZ, but the probability will be lower in terms of what the calculation accuracy it estimates it to be. So this is very valuable in terms of figuring out if Kinect is just guessing at a value or Kinect can actually see the value in person. But at this point, I'm not going to worry about W, so I'm just going to take the X and the Y. So what I'm going to do is this. I'm going to say head, or actually I'm going to say canvas. And this is why I chose a canvas, because canvas supports 2 properties called set left and set top that allows me to take the canvas and position it, or that allows me to take the ellipse and position it anywhere on the canvas. So I'm going to say canvas.setLeft. And now I'm going to say the element I want to set left is head, and the value where I want the canvas to be is skeleton.joints joint editor header position dot x. Okay, before I do this, instead of making the code too complicated, let me talk about one small thing. Okay, the value, like we said, of x that you get back is actually in meters between +1 and -1, depending on if you're to the left of the Kinect or right of the Kinect. Now, that doesn't really translate very well to the canvas resolution, which could be like 500 pixels by whatever, right? So the Kinect runtime offers a very cool method called, in Kinect.skeleton-engine, there's this very cool method called skeleton to depth image, right? If say for instance, you don't really care about the actual dimension of +5 meters or -5 meters, if all you care about is where is the head as it relates to the 320 by 240 depth image, you can use this method, right? And you will almost always use this method if you want to take skeleton tracking and show it on the screen for whatever reason. So I'm going to say skeleton to depth image, and you can basically see that it takes 3 values. It takes a vector for the exact point where the head is. It also takes 2 parameters, depth x and depth y, which are out parameters. You'll see it says out. Out means that the value will get returned in these. You know how a method or a function can only return 1 parameter? But using these out parameters, these are by reference parameters, if you will, where we return multiple values. So I'm going to show you how to use it, right? So I'm going to say float dx dy, and then I'm going to basically come in and say my location that I want to convert in a second. This is all going to make sense. Okay, so this line hopefully should make sense now. What it's doing is I'm using the skeleton to depth image call to provide the position, the actual position in meters of my head, and I want that converted into dx and dy as it relates to the 320 by 240 pixel. Now dx and dy are going to be a floating point number, as you can see, it's a float. It's going to range between 0 and 1. It's going to tell me at what percentage of the pixel is my head exactly at, right? So it's going to be between 0 and 1. So to get the exact position of where to place my head on this canvas, I'm going to look at this canvas right here and see that the height is 239. I'm going to make it 240 just for the math to be simple. And a lot. I'm going to make the height as 240 and the width is 503. I'm going to make the width 500. So now we have a 500 by 240 canvas. So what I'm going to do is I'm going to set the canvas.set left. I'm going to take my head position and move it to dx times x plus 500. And you sort of see where I'm going with this. Now I'm going to say canvas.set top. The same head position should be at dy times 240. Right? So I'm going to do the exact same thing. I'm just going to copy paste this code, if you will, for my hand left, and I'm going to take this position and move it to left. Okay, and then once more I'm going to take this code and instead of head I'm going to do hand right, and I'm going to take this and move the light ellipse. Okay, I think that should be it. Let's make sure everything is in place. So if skeleton.tracking state is tracked, then we first do a skeleton to depth image, grab the position of my head, then move it out to dx dy, and then move the head ellipse. Do the same thing for hand left, do the same thing for hand right. Okay, sweet. Let's hopefully there's no errors. Okay, here's my canvas. Here's me. I'm going to move sufficiently enough so you can see about 3/4 of me. Okay, I should calibrate it a little further because my head is far too low. It's funny, you know, oh, actually my hands are above my head. It actually makes sense. So see, you can actually, and right now I'm sort of off-center from the Kinect, so this is sort of the center. And so you see my head is in the center. So it's actually tracking. I mean, obviously you can assume that you have to fine-tune it a little bit in terms of scale and all of that. So right now it seems like I have to move my hands a lot. You're clapping already. You want me to end up, you know? And what was that? It seems like I have to move my hands a lot to get small motions in my hands. So you can actually work on scaling issues for that. So for instance, you know, if I say at 2 times scale, right? I mean, just this is a very crude estimate, but I mean, if I say for my left hand and for my right hand, I'm going to say give me 2 times scale, which means if I move my hand even a little bit, it'll move it a lot. Oh, it's moved out of. So yeah, I mean, there's ridiculous levels of jitter. So, but you get the idea. So you can basically, in spite of the scaling issues, you can basically see how simple the code is, right? You can basically call the event handler. It'll automatically get called for you, and then you'll get 6 skeletons, and for each skeleton you'll get 20 joints, and for each joint you can get its position in terms of x and y, which you can then convert back into screen coordinates and put it back on the screen. So that's literally, and if you look, this is very similar to the way we did image, you know, and depth frame data. So hopefully that makes sense. If you have any questions, obviously I'm happy to take, but this is all the content that I wanted to show. And this puts you in a really good position now to look at the sample code that comes with the Kinect SDK and to look at all of the other projects that Stuart talked about and take it from there. So with that, I'm sorry I ran out of time, and I sort of turn it back to you to take it from there. So with that, thank you so much, guys.
好，谢谢，非常，真的。